Hello, this is part 2 of the lecture on description, correlation and causality, and in this part we'll look at the idea of distributions. Now previously we had these two types of findings, and we're going to concentrate mostly on the first kind of finding where we're looking at the distribution of the values of a single variable. In the next part we'll look at the links between variables as in this finding. But for now let's think about a single variable, and distribution is the name we give to the overall pattern of a variable's values. It's quite useful to think about the type of data we're dealing with. So you might be dealing with nominal data such as the occupation of somebody, or their nationality, or their religion, and so on. And in that case you could describe the distribution of the data, for example using frequency tables, saying how many or the percentage in each category, and you can show that in a pie chart or a bar chart. Then if you had scalar data like age or income or weight, you could perhaps use a histogram, or a line chart would be another one. Here's an example of a frequency table with percentages shown for the Kenyan data. Here we've got different categories of migrants, including non-migrants, and you've got how many in each category and then the percentage. One obvious way to show it is in a pie chart. So here you've got the percentage in each category shown. Here, slightly more complex and interesting, is looking at the construction of houses. And in this Kenyan survey, bricks and stones are now the most common, but there's still about a quarter of people have still got mud houses. And then smaller sections for things like iron sheets, bits of wood, obviously, and informal settlements and so on. And there's a simple one, but it's struck me because even going back to 2009, already a survey of Kenyan adults said that 80% of Kenyan adults had their own mobile phone. If you bring that more up to date, it's getting up towards 100% now. I mean, very, very high, well into the 90s. In case you think this is all getting too simple, here's one that I found circulated via Twitter that the Times educational supplements supposedly printed. Last week we asked whether A-levels are becoming harder to pass, and you said, so you can work out whether or not that would get a high mark in QED. Now let's move on to some scalar data, and the scalar data we could look at is the Kenyan household survey data on expenditure on food items. So here we've got a histogram, here's thousands of Kenyan shillings. There are 10 here, so each one is 100. So that 0 to 100 is the most popular category with over 600 households. Then 100 to 200 has over 600 again. And it gradually falls away like this. There's a few households here with much higher expenditure on food. Here's the shape of the distribution for ages. So this is 30 to 32, 32 to 34 and so on. So the most popular categories are around about 30 here. I think it's 28 to 30 is the highest frequencies. Here's the mode, and the mean is around about 34. Now we can describe the shape of distribution using these kind of words. Symmetrical should not need much explanation. But symmetrical would be a shape something like this. It's hard to draw exactly with a pen, but more or less. So the idea is you've got a mean somewhere here, which should also be, in this case, the mean and the mode would both be here. And then above and below this, the shape is very, very similar each side, so it's symmetrical. Whereas with skewed distributions, what you've got is quite a big bulk towards one end and then a long tail off, which is much longer in one direction than the other. So that's one possibility. And here's another possibility where the long tail is on this side and the bulk of the observations are relatively high. How to remember which one is positively or negatively skewed? Well, there is a complicated maths formula which you can look up in a book if you really want to, but the much easier way to remember it is that if you turn this one on its side, you get a P. So this one is the positively skewed one. This one is negatively skewed. Unfortunately, if you turn it on its side, you get a B rather than an N, so that doesn't help. But if you remember the P, that will help you remember which one is positively skewed, I hope. Here's an example of one which is fairly symmetrical. There's not really an obvious skew to either direction. It's reasonably well balanced around the mode, which is the highest category, and the mean, which is close in here. So that's the shapes of different distributions. Now let's look at some descriptive statistics. Descriptive statistics has a couple of meanings. First is the overall area of statistics, where you look at the values that you actually have in your sample. Sometimes we want to look at the sample and try and work out what that tells us about the population. In fact, that's what we do most of the time. And that problem of looking at a sample and working out what it tells us about the population is known as inferential statistics. But when we're just trying to describe the numbers we actually have, that's called descriptive statistics. But in this slide, I'm using descriptive statistics really to mean the particular numbers, like the mean as a statistic and the median or the standard deviation. So those particular statistics as in numbers that help us describe things. So here we've got the mean, the median, and this trimmed mean. Well, the median, you should know, is the number in the middle, and that's quite good because that's not affected so much by extreme values. For example, if you had a village where the median income was sort of around about $2 or $3 a day in the few hundred people that lived there, then the mean would probably be similar to that if there weren't too many extremely very, very poor people or especially very rich people. But if a very wealthy person, like for example the boss of Amazon, Jeff Bezos, was to come to that village and live there for some reason, then suddenly the mean income would shoot up into the millions and billions of shillings, whereas that would be a meaningless measure. That would no longer reflect the lives of most people in the village. That would just reflect his life. Whereas the median would hardly be affected when someone like that moved to the village, because it would just move up to the next person in order. So because of that, if we're worried that the extreme values are going to affect the measurements, then the median is a better choice than the mean. Or an alternative is to use something like the 5% trimmed mean, and that's saying that if you have some values like this and then just a few extreme values which might be pulling the mean away from the general distribution here, what you can do is use a 5% trim mean, so it takes off the bottom 5% and the top 5%, maybe not this one, and that just work out the mean of the ones that's left, and that has less of a destabilizing effect than it does if you include these here. So we've got the examples for the Kenya survey and for this rainfall data in Mali, Sugu, and you can see that in all cases the mean and the median are sort of closest, except not quite the same. The mean is generally above, and the mean is a long way above the median in cases where there's a very positive skew, because there is a case, the very positive ones are where you do have a few values that are much, much higher than the general distribution, and that pulls the mean well above the median. So in that case, you can either stick to the median or recalculate the mean, excluding the 5% extreme values, and then in that case you find that in all of these examples, this comes back much closer to the median than the mean. So that's quite a good alternative to using the mean when you have extreme values or outliers. So the mean and the median and the trimmed mean are a good way of describing the level of a distribution. Sometimes we also want to describe the spread of the distribution. So for example, if we're concerned with inequality within a society. Standard deviation is the most commonly used measure, so that's the one we'll focus on most. But there's also the range and the interquartile range, which also have advantages. Standard deviation, though, we use most of the time, and it's written with this sign, which is sigma, and this is just the Greek letter S, the small Greek letter S, standing for spread, standard deviation or spread. Now, a really useful rule of thumb, without doing any fancy calculation, you can work out that for any distribution, almost all the individuals, which could be individual people or individual households or individual years, almost all of them are going to lie within 2 standard deviations of the mean. And this works for anything, but especially when it's quite symmetric. And when it follows the normal distribution, which we'll discuss quite a lot this semester, then you can work out exactly this percentage of the individual values are within 2 standard deviations of the mean. So let's just show you that on these examples we had already. So here's the graph of the Kenyan food expenditure. So let's just work out where the mean is. That's this mu here, 2451 is 451 is around about here somewhere. Interesting. Okay, that's mu. Oops. And what the rule of thumb tells us is that if we double that, So 2 times that is approximately 2 times that, which is as near as 9,000 roughly. So that's 2 of them. So if we start from here and we subtract 2 of those, so that's this minus about 9,000, we come down to about here. And if we start from here and we add on 2 of those, so add on 9,000, we go from 2,451 up to about almost 12,000. So that's this way. And this range here is going to contain almost all the values. And you can see there's just a few that sneak out there in this very skewed distribution. But almost all of them are captured in here. Next diagram shows the same thing works out for these values with the ages. So here the average is 34, which is around about here somewhere, isn't it? So the means, how you can see the mean is going to be slightly above the mode, which is here. And if we double this, we get about 18. So this plus this minus about 18 take us down to there, and the mean plus about 18 takes us up to there. So these are the 2 extremes here. So most of the values are within this range, and there's again just a few left out there. And finally, this is the one where it would work more or less exactly, is that starting from a 2055, the mean, wherever it is, around here somewhere, that's your mean. Double that, you get about 1,400, roughly. So start from here, subtract 2 of those, you get down to 610. Start from here, add on about 1,400. Oops. You get up to about 3,500. So it would be quite close to 95% or 95.45% of the value is going to lie in this range, because it's quite a normal looking distribution. Okay, so that's a useful rule of thumb. And finally, I've got one more example in words here. If you knew that in a certain Bangladeshi area, if you're told the mean catch is 37.2 kilograms, then you might wonder, well, yeah, okay, but do some people do a lot better than that? Some do a lot worse. That's the mean, but it doesn't tell me about anything much more than that bare fact of being the mean. But if you have this information as well, then you can double this, and you get 2 times 8.2 is 16.4, and then use the rule of thumb. So subtract this from the mean, and you get down to 20.8. Add this on to the mean, and you get up to 56.3. So 37.2 plus or minus this gives you this range. And we can tell that almost all the boats are going to catch between this much and this much each day. So it gives us a much better feel for, okay, what's the experience of people living in that area catching fish. Okay, the best of them are going to be around this much, and the less fortunate ones are getting around this much, which gives you more information than just knowing the mean is 37.2. So that's how we can use the rule of thumb in descriptive statistics to tell something about where the bulk of the observations are.